Good afternoon, everyone. We'll be starting class in about 1 to 2 minutes time. Good afternoon, everyone, and today's class is going to be focused on the topic of block diagram simplification. In particular, when we have a very complex block diagram and we need to reduce it in order to obtain the overall system transfer function, we're going to be looking at certain strategies that we can use to reduce the block diagrams, as well as certain techniques that assist us with reducing these block diagrams in particular in today's lecture. Once this lecture is finished, we'll be moving on to the selected questions and problem set 2 that everyone voted on, and I'll be doing the top 3 questions that got the most votes from the poll on My Learning. So typically, whenever we're dealing with engineering systems, they tend to be somewhat complex in nature. They never tend to be simple, and as such, you can see that there will be like several interconnections here and there, and then like connections in between other systems and so forth. And the question is, when you have something that looks this complex, how do we simplify this in order to get an overall transfer function mapping our outputs here, y of s, to our input, x of s accordingly? And that's what we're going to be focusing on in today's lecture, the techniques and the strategies used in order to reduce this into one simple block that represents the entire transfer function mapping y of s to x of s. So we were first going to look at the techniques that we'll be using in particular for doing the block diagram reduction process. So the first technique we'll be looking at is if we move a takeoff point from the right here to the left here accordingly. And in moving this takeoff point, once we move it from the right of a system block to the left of a system block, in order to compensate for it, that means this new takeoff point here must be multiplied by the system block in order to achieve the same equation. And the reason for this being is, let's watch this from a mathematical standpoint. So y1 of s is equal to x of s by h of s. And y2 of s in this case was also equal to x of s by h of s. And when we shift this towards the left, we need to make sure that our y1 of s equations and y2 of s equation remains the same. And in order to compensate for this, that's why we need to make sure that our y2 of s equation to be the same, equal to x of s, h of s. We need to make sure that when we move this takeoff point from the right here to the left, we multiply by the block that was shifted across. So as of such, once this takeoff point moves from the right of the h of s block to the left of the h of s block, the compensation in order to maintain the y2 of s equation is that it needs to be multiplied by this h of s block here accordingly. And the reason for this is that we need to maintain our original equations here for y1 of s and y2 of s at this point here as well, for the takeoff moving from right to left. Let's say if we do it the opposite way, we're going to be moving the takeoff point from the left of the h of s block to the right of the h of s block. So we're going to have to observe this using our system equations again. So y1 of s here is equal to x of s, h of s. Or y2 of s here is equal to x of s. And when we move this towards the right hand side here, we see that in moving it from the left hand side to the right hand side of the h of s block, the compensation is that we need to be 1 divided by the h of s block here in order to maintain the y2 of s equation. Reason for this being is, if you watch what our equations here are, the y1 of s equation here, oh, oops, sorry. The y1 of s equation here is x of s, h of s. For the y2 equation here, if we actually follow the flow, you can see it's x of s, h of s here, but we need to make sure that y2 of s is equal to x of s. So now to get back that x of s alone, we need to divide by h of s accordingly to get back to our equation. So this here would be x of s, h of s, all divided by h of s, and these h of s here cancel. We get this back equal to x of s. So are there any questions regarding moving the takeoff point from the right to the left or to the left of the right of a system block in particular? Right, so the reason why we divide by h of s here, let's watch the system flow here. Right, so, and let's go back a little bit. Right. So, if we watch our original system block here, for y1 of s and y2 of s, but the takeoff point is on the left, y1 of s is going to be x of s multiplied by h of s, which gives us our equation here for y1 of s. And y2 of s, because it bypasses the h of s block here, is equal just to x of s accordingly. When we move from the left of the h of s block to the right of the h of s block, we need to maintain our equations here for y1 of s and y2 of s. So y1 of s here is still x of s multiplied by h of s, just following the straight flow here. For y2 of s, we need to make sure that it's equal to x of s. But if we watch y2 of s here, and let's say we ignore this 1 on h of s block for the meantime, it's going to be x of s multiplied by h of s. And in order to get this back to just being x of s, we need to divide x of s by h of s here by h of s as well. So this comes like x of s multiplied by h of s multiplied by 1 divided by h of s. And the h of s's here will just cancel accordingly to just give us back our x of s signal. So yes, it's basically just h of s multiplied by 1 divided by h of s to get back only the x of s signal that we had in starting here in particular. So the trick when you're doing it with takeoff points is that you need to make sure you know what the original equations are to begin with before you do the takeoff shifts. And then when you actually do the shift, what are going to be the compensations you achieve by adding an extra block when you shift accordingly to get back the original equations for y1 and y2 of s here as of such. So always start with before you actually shift the point here to obtain the original equations for y1 of s and y2 of s, and after you shift it, be it left to right or right to left, then you need to make sure that you maintain the y1 of s equation as is, and then the y2 of s equation as is as of such. And in most cases, the y2 of s equation is where you're going to be adding in an extra block on this takeoff point exactly when you do the shift, in order to get back to the original y2 of s equation as of such. Are there any further questions regarding takeoff point shifting? Alright, looks like we don't have any further questions regarding this. So let's move on to the next thing in particular for our techniques. So our next technique that we're going to be looking at is moving summation junctions instead of takeoff points. So we're going to have to watch what happens there when we move a summation junction from the right of the HFS block to the left of the HFS block. But we're doing the same thing as before, that we need to maintain what's going to be our YFS equation here for the output of the summation junction, as is, or the output in this particular case for the entire block diagram here. So if we watch the YFS equation here, we can see here that at this point in particular, this is going to be x of s here multiplied by h of s. And then for this point here with our v of s, this is going to be minus here. And because it's a summation junction, this will be positive x of s, h of s, minus v of s. And this is the equation that we want to maintain after we shift this summation junction from the right of h of s to the left of h of s. So let's move it towards the left of the h of s here and see actually how do we compensate to get back this original y of s equation. So in moving the summation junction from the right to the left, that means that the affected block being h of s, we compensate this by saying it's 1 divided by h of s to get back our y of s equation here. And let's actually work out the math for this to see if this is true. So we're going to introduce a temporary signal here, and we're going to call this e of s. So at the output of y of s here, this is going to be h of s, e of s, because we're considering only the outputs at our summation junction here. And so the question that we're going to ask is, okay, because we know what y of s is here in terms of h of s and e of s, what's going to be e of s here? So e of s here, we can see that x of s is positive going into the summation junction, so we say this is x of s. And then we have a minus sign here for v of s. So this is v of s divided by h of s, and it's going to be minus. So v of s divided by h of s. And then if we substitute this into our y of s equation, this is going to be h of s here into x of s minus v of s, h of s, raise this, and if we expand out the brackets, we basically see that y of s here is going to be h of s, x of s, minus v of s, which is basically the same equation that we had to begin with. So in moving a summation junction from the right of the h of s block to the left of the h of s block, the compensation that we do in doing that shift is that we need to have 1 divided by the h of s block here accordingly, in order to maintain our original y of s equation that we had to begin with. Now let's watch what happens when we move the summation junction from the left of the h of s block to the right of the h of s block accordingly. And we're also going to watch the math for this as of such. So let's introduce our temporary signal here as well, named e of s. And we can see here that y of s is basically e of s, h of s. And we need to figure out what e of s here is in terms of x and v. So e of s, oh, whoops. So e of s, yep, making mistakes because I need to compensate for that, right? So we're saying e of s here is equal to, and we can see here x of s here going into the summation series is positive, so we say x of s, and then the v of s here is negative, so minus v of s. So y of s here, if we substitute in e of s, it's just going to be h of s into x of s minus v of s. So yeah, E of s is the summation of x of s and v of s because of the summation junction. Yeah, I think I just explained that as well, as of such. So we have our y of s equation here before we move the summation junction from the left of h of s to the right of h of s. And we need to maintain this equation after we do this move from left to right. So in moving this, that means the compensation is such that in moving the summation junction from the left of h of s to the right of h of s, we need to make sure that the block compensation here is going to be the h of s block as of such. And let's watch this mathematically to see if this actually is compensated. So I don't need to put an intermediate signal here or a temporary signal here because this is just going to be straight up y of s. So y of s here, as you can see here, is x of s multiplied by h of s here, and it's going to be positive here. So that's x of s, h of s, and then for the negative part of the summation junction here, we have v of s multiplied by h of s, and that's going to be minus v of s, h of s. And we can see that basically it's the same equation that we had to begin with before we move the summation junction from left to right accordingly. So in moving the summation junctions and moving the takeoff points, all you just need to begin with is the output equation after the h of s block before you do those moves. And once after you do the moves, if you can maintain the output equations as of such, you will know how to get the compensatory blocks in as of such to make sure that you have the same equations after you do your moves for your takeoff points and for your summation junctions as of such. Right, so is there anything in particular that I need to review with moving the summation junctions that was unclear? Alright, doesn't seem that we have any questions for moving the summation junctions. So those four techniques that you saw here are for moving the takeoff points left to right and right to left, and moving summation junctions left to right and right to left accordingly. Those four techniques are what are going to be the basis for what you're going to use when you're reducing complex block diagrams into a simple block diagram as of such. So it's important to remember these four techniques for the reduction of block diagrams. So we're now going to actually apply our techniques that we just now saw here into an actual example where the block diagram here is somewhat complex in nature. And I know we have Laplace equations for G1, H1, H2, and G2, but we're going to be substitute this at the end after we do all our reductions in order to get everything in one fell swoop. So before I start, there is no one way to reduce a complex block diagram. There are several ways to reduce them. Whichever way you start with, it's perfectly fine. There may be some ways that may be a little bit longer than others, but all of these ways will be carrying the same marks throughout, as well as the evaluation for these kinds of questions will be more on the technique and the approach rather than the final answer when you're doing block diagram reduction in particular. So there's no one way to approach this problem. There are several ways to approach this problem when you're reducing it, and all ways are perfectly fine. As I say, some ways may be a little bit shorter than others, but whichever way is most comfortable for you when you're approaching this, it's perfectly fine to use any of those ways. You will not be penalized as of such. So the first strategy that we are going to be observing here when we combine these with our techniques that we just now saw is that when you're reducing block diagrams, the trick is to try and get rid of all these summation junctions. And in getting rid of these summation junctions, that means we're trying to make these into feedback systems as of such. So either negative feedback systems or positive feedback systems. And once you have those, as we saw in yesterday's lecture, we can just reduce the summation junction and the G and H blocks here into one full block, which we're going to be seeing in today's lecture for our simplification process as of such. So the next few slides are going to just show you a general approach that you can take for simplifying this example block diagram that we have here. So the first step that we'll start with is that we'll move this takeoff point here connecting H of 1 from the left of G2 to the right of G2. Now, as we saw, when we move a takeoff point from the left of a block to the right of a block, the compensation is that we're going to have to divide by that block that is affected. So in moving from left to right of G2 and only G2, that means the compensation here is going to be 1 divided by G2 as of such. The next step would be that we observe that in moving that takeoff point, we now have a negative feedback system here accordingly, where our feed forward path here is the G2 block, and our feedback path here is the H2 block. We saw from yesterday's lecture that for negative feedback, the general transfer function will be G divided by 1 plus GH accordingly. So this summation junction here and the G2 and H2 blocks here can reduce down into that transfer function, which will be represented by one block here, which you can see here shaded in orange. So just to highlight this back, this being here a negative feedback system, the feed forward part is G2, and our feedback path here is H2. And as we saw from yesterday's lecture, the transfer function for a negative feedback system is going to be G divided by 1 plus GH. So as of such, this is going to be G2 divided by 1 plus G2 H2. Our next step is to move this takeoff point from this point here to this point here as of such, because we want to make sure that we also have another negative feedback system here as well, but we can't have any summation junctions or takeoff points in between for us to reduce this and get rid of the summation junction. So in moving this takeoff point from the left of this block here, the G2 divided by 1 plus G2 H2, to the right, Our compensation would be that we need to be 1 divided by that block as of such. So we just invert this accordingly, and we get 1 plus G2 H2 divided by G2 here as of such. For people who may be questioning, why do we have H1 divided by G2 here? We had H1 here multiplied by 1 divided by G2 as of such. So that's why we get H1 divided by G2 here as of such. Now that we actually move that takeoff point here from left to right, this part here is also a negative feedback system, where our feed forward part here is represented by our G1 block here, and our G2 divided by 1 plus G2 H2 block here, and our feedback path here is H1 divided by G2. So we can say here that the multiplication of these two blocks here will generally be our G, and our block here represented our feedback is going to be H. So we reduce this feedback system accordingly using our general negative feedback equation, which is going to be G divided by 1 plus GH. And after we do all the math and so forth, we get this entire feedback system here reducing into one block here, which is going to be G1 G2 divided by 1 plus G2 H2 plus G1 H1. Our last step here in eliminating this last summation junction is that this is going to be a feed forward system, because this doesn't go backward towards our input. All of these are just going towards our outputs here accordingly for y of s. So when we have a plain line here that's just that doesn't have a block, we say that the value here is just going to be 1. And because the value here is 1, and this being a feed forward system, this means that it's going to be 1 plus G2 H2 divided by G2. And if we unify the denominator here, so let's actually write out that equation for you guys to see all this. So this here will resolve to 1 plus G2 H2 divided by G2. And if we basically unify the denominator, this comes like this: G2 plus 1 plus G2 H2 all divided by G2. So this equation here, because of the feed forward system, reduces to this transfer function that we just now obtained, which is represented by this orange shaded block. And our last step would be to just multiply the two blocks here accordingly, and we get our final transfer function here mapping y of s to x of s. So our transfer function is obtained in reducing the entire block diagram from a complex version to a simple version, which is just represented by one block. And for your homework, I'd like for you guys to substitute the G1, G2, H1, and H2 equations that we saw at the start of this problem, and then try to simplify it down to a proper fraction. As of such, there shouldn't be any fractions on the numerator or the denominator as of such. It should only be whole or decimal numbers on the numerator and on the denominator. So is there anything I need to go back through in particular for this first example that may require some additional clarification or further explanation as of regarding any of those steps? Okay, yeah, sure. I could go back through that. So, in reducing the feed forward system here, the reason why it's feed forward is because watch the directions of the arrows. The arrows are all pointing towards the output, and the output in this case would have been y of s. So let me write in that y of s here for you. Hold on. Right. So, in reducing a feed forward system, it's a lot simpler than reducing the feedback system because for the feedback system, as we saw in yesterday's lecture, it involves watching the summation junction and then compensating for it accordingly to get our transfer function. But for a feed forward system, it's just the addition of the two blocks here as of such. Now, if there isn't a block on the line for the feed forward system, the value of that line is going to be unity, or what we refer to as 1. So because this line here doesn't have a block, we say the block that's supposed to be here is supposed to be just a value of 1. And because it's feed forward, this comes like if it was similar to our parallel interconnection that we saw in yesterday's lecture. So once we have a parallel interconnection, that means we just add the blocks accordingly in order to get to the output here. So for our feed forward system here, because we just have this line and we say, okay, this is a value of 1, this is going to be 1 plus this block here, which is going to be 1 plus G2H2 divided by G2. So we get this 1 here representing this line, and then we add this accordingly to 1 plus G2H2 divided by G2 as of such. And then we just want to make G2 a common denominator throughout the entire thing. So that means that this 1 here, to get back this value, we need to make sure that it's going to be G2 here accordingly. Because if we cancel G2 here and G2 here, we'll get back this 1 value here. So in unifying the denominator for this addition, it's just going to be G2 plus this entire numerator here, 1 plus G2H2, all divided by G2, and reducing the feed forward system. Right, so that should hopefully explain the reduction of a feed forward system, because it's basically just a parallel interconnection where you just add each one of the blocks on the lines together as of such. For a feedback system, on the other hand, though, the feedback system involves the use of the temporary signal in order to obtain the actual transfer function, which we saw in yesterday's lecture. So no, they are not the same for reducing the feed forward and feedback. The reduction of a feed forward is just adding the blocks together, or because the direction of flow here are all pointing towards the same direction, being towards the output. But for the feedback, which we saw in yesterday's lecture in particular, it's because one line is going to be pointing towards the output, but the other line is going to be pointing back towards the input. So the reduction strategy is totally different for a feedback system. And no, they are also not inverses of each other. They are two different approaches altogether. Right. Do we have any further questions regarding this first example here? Alright, so it doesn't look like we have any further questions. So like I said, for this reduction that we did here, because we had S-domain equations for G1, G2, H1, and H2, for homework, you guys need to substitute those equations for each one of those G and H's here, and then simplify the answers to actual proper fraction. Meaning that there shouldn't be any fractions present on the numerator or on the denominator. It should just either be whole numbers or decimal numbers only, if required. And your second homework here would be to attempt and simplify this following block diagram as of such. And like I said, the trick behind this is that you want to keep on getting feedback systems or feed-forward systems to reduce such that you can eliminate these summation junctions as of such. And a good idea how we can actually start approaching this problem in particular, if we watch this takeoff point in between G2 and G3, mapping H1 here, we can see that if we move this from this point here to the right of G3 and we put it like all the way across here, G2, G3, and H2 represents a negative feedback system which can be immediately reduced as of such. And then you can just keep on doing the same strategies here for your feedback systems to keep on reducing them, or if you have a feed-forward system, you can do the same thing as of such. So the trick is to always try to get some feedback or feed-forward system which you can reduce to eliminate the summation junctions one by one, and to remember the 4 techniques that we saw in the starting of today's lecture for moving takeoff points left to right and right to left, as well as moving summation junctions from left to right and right to left as well. Once you employ the strategy of getting rid of those summation junctions and using those 4 techniques, you can apply this to any block diagram that you will ever encounter throughout the entire grid. And the third thing I'd like for you guys to try here, and this one's a little bit more simple, is to actually obtain the y of t signal here. But in this case, we're going to have a disturbance signal d of t being added in between our 2 blocks here, c of t and h of t. So for this particular homework, you will have to use the technique that we used in yesterday's lecture to obtain the transfer function for the negative feedback system. So you want to use the same technique that we used there to actually get this output y of t equation with respect to r of t and d of t as of such. So I did give you a little bit of hints here, and well, you could have just transferred the entire t domain, the block diagram, into the s domain. And like I said, just use the step-by-step approach from lecture 13, which we did for deriving the negative feedback system equation, in order to obtain the transfer function for this homework problem here. And you can either represent the answer in the Laplace domain or in the time domain, either way is fine. And for verification, to see if you're going on the right step, this is actually going to be the answer for the third problem here for your homework. So you can see that when you actually attempt it yourself, if you actually get to this answer as required. Alright, so that basically brings us to the end of our block diagram simplification lecture. Basically what we saw is that the general strategy is to get feedback systems or feed-forward systems where we can eliminate those summation junctions one by one. And in order to do that, we need to employ the 4 techniques that we saw in today's lecture, being moving the takeoff points left to right and right to left, as well as moving the summation junctions from left to right and right to left accordingly. And in doing the general strategy, which employs these 4 techniques, you keep on eliminating each one of the summation junctions, and slowly but surely you get down to one final block that represents the entire system transfer function from the output y of s to the input x of s accordingly. If there are any further questions regarding the contents of this lecture, please ask them now. Alright, so looks like we don't have any further questions. So if there are any other questions that you guys need to ask, please ask them in the comments down below. Or you can email me those questions accordingly regarding the contents of this lecture. So at this point, we're going to be moving on towards the selected questions for problem set 2, which you guys voted on My Learning. And we will be doing the top 3 questions that had the highest amount of votes accordingly. So let's close this off for the time being. Bring up problem set 2. See if I can get the web page up here to show you guys the responses. Well, I did write them down accordingly. So it seems to be loading properly. Okay, so these are the responses from what we obtained regarding our poll for the questions to be done live for problem set 2. And as we can see here, question 4 is the highest with 10 responses, followed by question 10, which had 9 responses, and question 12, which had 8 responses. So I'll be doing question 4 first, then question 10, and then question 12 accordingly. Of My Learning. A little bit. So question 4 asks, for this resistance capacitance network that we observe, we need to obtain the differential equation related to y to x. And then if the instant voltage on the capacitor is 1 volt, and we have x of t is equal to 2 to the e minus t, we need to find what's the y of t equation using the Laplace transform accordingly. So I'm going to have to bring up the whiteboard here to actually start this. We still had some working. We had some working from the last day. Play the entire canvas. Switch that accordingly. Second. Alright, so in starting question 4, we basically knew what circuit diagram was. We can basically apply Kirchhoff's voltage law in order to obtain an equation in an integral form here for x of t. And in doing so, this comes like we get x of t here is going to be equal to I by R because of that resistance, plus 1 divided by c integral of I dt. And let's call this equation 1. And we also know that if we say the entire current flowing through the circuit is I of t, we just only want the voltage across the resistance, which is going to be our y of t. y of t is basically just going to be I by r. And let's call this equation 2. So we can manipulate this accordingly, and we get I equal to the subject of the formula being y of t divided by r. Let's call this equation 3. So if we substitute equations 2 and 3 into equation 1, we can get our equation here being x of t is equal to y of t plus 1 on c integral y on t divided by r of dt. And we also know that r is equal to c here is equal to 1, which is what's given to us in our starting question. As we see in our diagram, c was 1 and r was 1, so we substituted in those values accordingly. So we get x of t here is equal to y of t plus integral of y of t dt. So we have an equation here mapped in integral form, but ideally we would like to get this in differential form. So what we'll do here in this particular case is that we'll differentiate the equation once. So as of such, we'll get x prime of t equal to y prime of t plus y of t. And this satisfies an equation here for mapping our inputs here to our outputs. And let's call this equation 4 for the time being. So for the second part of the question, it asks for if the instant voltage on the capacitor is 1 volt, and if x of t is equal to 2e to the minus t, we need to find y of t using the Laplace transform. So because we have a differential equation here mapping x and y accordingly, let's take the Laplace transform of 4. So LT of equation 4. And I'm going to put the y's on the left hand side of the equation and the x's on the right hand side of the equation. So y prime of t here will become s y of s minus y of the initial condition plus y of s is equal to x of s minus x of the initial condition. And let's call this equation 5 here. And we also know that x of t is equal to 2e to the minus t. So at this point, because we have our Laplace transform equation of equation 4 mapped as equation 5 here, we have x of t equal to 2e to the minus t. We need to make some assumptions here that wasn't given to us, to say that assume initial conditions for input and output. Oops. Zero. So that means y of 0 negative is going to be equal to x of 0 negative equal to 0. I make that assumption? No, I can't make that assumption for the inputs. Oops. So I can't make that assumption for the inputs because we actually have x of t equation here. Assume initial conditions for the output. Equal to 0. But however, because we have our x of t equation here, if we actually watch for x naught, this is going to be x of t as t tends towards 0. And that will become 2e to the power 0 here, which will give us a value of 2. So what happens here is that because we have this here being a value of 2, we also can't assume an initial condition for y naught here, because we also had the voltage across the capacitor. So we can't assume those initial conditions for y naught because of the x naught condition. And this is true because the question basically gave us the instant voltage on the capacitor being 1 volt. So we need to factor this in accordingly for our y naught at this point. We can't make that assumption because of that initial voltage, which I initially forgot about. So at t equals 0, capacitor voltage is equal to 1 volt. And if we watch the voltage of y naught being the voltage across the resistance, this is basically going to be the voltage of the capacitor being factored in here with the initial voltage of x naught. So the difference is going to be x naught minus dc. It's going to be 2 minus 1 close to 1. So now we actually have values for x naught here and y naught here. We can substitute these x naught values here and the y naught value here into the equation above, equation 5, to obtain our actual Laplace equation as such. So substituting x naught and y naught into 5, this will give us s y of s minus 1 plus y of s with the s x of s minus 2. We can factorize out the y of s on the left hand side. S plus 1 is equal to s x of s minus 1, because we carry across that minus 1 from the left hand side onto the right hand side. And as of such, we can get y of s here is equal to s x of s divided by s plus 1 minus 1 divided by s plus 1. Recall x of t here was 2e to the minus t. So that means x of s here, when we watch our Laplace transform table, is going to be 2 divided by s plus 1. And if we substitute that in accordingly, that becomes y of s is going to be equal to 2s into s plus 1 all squared minus 1 divided by s plus 1. And let's bring this down to a common denominator. So we want the denominator here to just be s plus 1 squared. So we say y of s is equal to 2s into s plus 1. Oh, sorry, it's going to be 2s, my bad. 2s minus 1 to s plus 1, all divided by s plus 1 squared. If we expand this out, we get y of s is equal s minus 1 divided by s plus 1 squared. And in partial fraction, this will be similar to a divided by s plus 1 plus b into s plus 1 all squared. So let's actually use our partial fraction calculator to resolve this for us. So our equation here is going to be s minus 1 divided by s plus 1 all squared. So we say s minus 1 divided by s plus 1 squared. And we use our partial fraction calculator here to get all the steps as of such. And basically see that a naught here, zoom in a bit. So that resolves into a naught s plus 1 plus a1 over s plus 1 all squared. a1 here will resolve to minus 2, and a naught here will resolve into a value of 1. So basically, y of s here will resolve into 1 over s plus 1 minus 2 into s plus 1 all squared. And then let me bring up the Laplace transform table here. If we watch our Laplace transform table here, we can see that for anything that's s plus 1 and s plus 1 all squared, the associated Laplace transforms will basically be our exponents here. So this will be for e to the at being 1 divided by s minus a, but in this case we will have e to the minus at here as such. And then for our next transform here currently, we'll be watching this for when we have our factor here being s plus a all squared. So I'm looking for this on the transform table. Right, and the next one here will be this factor here, which is going to be n factorial divided by s minus a of n plus 1 here, as of such. This suits our second part of the equation, which is 2 divided by s plus 1 all squared, because this basically is going to be our value here for 2 divided by s plus 1 all squared. So this maps back to our transform here of t and n e to the at. So from watching our transform table, we can basically see that y of t here is equal to e to the minus t minus 2 because we're watching this as a constant, and we'll say this is t e to the minus t. And that actually gives us our y of t equation. Now, I'll bring back up the transform table here only to show you guys why this is so. We're factoring out this 2 here, so we get 1 divided by s plus 1 all squared. And n here is going to be 1, so that's 1 factorial will just give us 1. And then n plus 1 here will be 1 plus 1 will give us the squared value. And s minus a here is actually just going to be s plus a, so that's s plus 1 accordingly. And this will become t to the power n of e to the minus at, because this value, this sign in front of a here changes. So n here was 1, so that's going to be t to the power 1, which gives us t. And then e to the at here, because this was positive 1, this is going to be e to the minus at, so that's going to be e to the minus t accordingly. So that's how we get t e to the minus t, and we just factor out that minus 2 here, which is going to be our constant or our transform. So that basically brings us to the end of question 4. Are there any particular questions regarding the solution of question 4? In particular, you will not get a question like this in the final exam. This question is more of a practice question regarding the circuit analysis. But for the Laplace analysis, it started from like when we had the differential equation here, and moving towards the Laplace form. A question like this could come where we have the differential equation and they ask you to solve for it using the Laplace transform and then the inverse Laplace transform afterwards. And they will typically give you the initial conditions being y naught and x naught as of such. If a question like this does come in the final exam, it's somewhere worth between 8 to 10 marks of the 100 marks in the final exam. And the mark breakdown will normally be assigned more towards the working than the final answer. The final answer will just be only worth like 1 out of the 10 marks, if it's worth 10 marks. If it's 8 marks, it's still going to be 1 of the 8 marks accordingly. So the entire approach is what you're going to be getting the majority of the marks on regarding these kinds of questions. Okay. Any other further questions? Yeah, once we have time, I'll do question 11. I believe it's on the way in the series of questions because the next question I need to do is question 10. So yeah, once we have time, I will do question 11 accordingly. See what question 1 was. Question 1 is very straightforward, so the solutions I will post up after I finish will have the solution for question 1. I don't really need to do this, it's explained properly in the solutions that I will post up afterwards. But I will do question 11, which is a little bit tricky when you're watching the find of x of s and sketch the pole zero plots on the region of convergence. Alright, so the next question we're going to be doing is question 10, which is that to derive a differential equation relating y of t here and x of t for this block diagram. Alright, so because we have an e of t signal here, we're going to actually obtain an equation for e of t by considering the inputs of the summation junctions here as of such. So let's clear the whiteboard here. And I'm going to have to split the screen here for this one. So yeah, I'm going to have to split the screen for this one to explain how we're going about this. Right. So we want to try to obtain our equation here for e of t according. Watching the inputs here of the summation junctions that formulates the output here for e of t. So in watching this, we basically say e of t here is going to be equal to, let's watch this part here first, which is going to be a1 mapping back here. Sorry, no, let's watch this point here first. So we're watching this for a2 here mapping back to our negative part here. So it's going to be minus a2y of t. So I'm just going to say a2 of y. Then let's watch this part here, which is going to be just positive x of t. And then let's watch this part here, which is going to be, this part we know here is omega t going back here, so it's going to be a1 omega t, and the sign here is negative. So it's going to be minus a1 omega of t. If we watch our omega of t signal here, this is just going to be the integral of e of t. So, w of t is right, omega. So, omega of t here, integral of e of t. And if we differentiate this once, we'll get omega of t, omega prime of t, sorry, is equal to e of t. If we watch our y of t signal here, just following the general trend, and we already have our omega of t signal here, y of t is just going to be omega of t, and then we just integrate that accordingly. So we say y of t here is going to be the integral of omega of t. And if we differentiate this once, we get y prime of t is equal to omega of t. So let's call this equation 1, call this one equation 2, call this one equation 3. So equation 2 here is basically e of t, and equation 3 here is basically omega of t. So if we substitute equation 2 here into 1, and equation 3 here into 1, e of t here, I have to bring this up a little bit, e of t is omega prime of t equal to minus a2 y of t plus, we had our x of t signal here, minus a1 and we know omega of t here was equal to y prime of t. So the right hand side of our equation here at this point, and well, I can maximize this, get some space, has been resolved in terms of y and x. But the left hand side of our equation is y prime of t. Sorry, omega prime of t here accordingly. So we need to get rid of this omega prime of t here. And in order to get rid of this, is that if we watch equation 3 here, and we differentiate this once more, you get y double prime of t is equal to omega prime of t. And let's call this equation 4. And if we substitute 4 here, this part here, that means our resulting equation now becomes y double prime of t equal to minus a2 y of t plus x of t minus a1 y prime of t. Let's make x of t the subject of the formula. So x of t here will now become, make sure I'm doing this correct. X of t here will now become minus y double prime of t minus a1 y prime of t minus a2. Oh, wait, no. I'm transferring this all across. Right. X of t remains on its own side. Right. Okay. That's correct. So this becomes y double prime of t plus a1 y prime of t plus a2 y of t. Right, and that gives us the mapping of x of t to y of t here for our problem. So are there any questions regarding the approach here for question 10? Yeah, there's some of the content in yesterday's and today's lecture that simplifies stuff considerably when answering these questions. Alright, so because question 11 is on the way here, I'll actually do question 11 as of such. I will not sketch the pose zero plots, however, because in the interest of time, these are actually provided to you in the solutions. But I will explain how it is that we obtain those plots accordingly. Actually, no, I can't sketch these for you. Yeah, okay, yeah, I'm watching the wrong thing. Yes, I can sketch the pose zero plots for you guys, and the region of convergence as well for these. So let's start with part 1, which is going to be x of t equal to e to the minus 2t u of t plus e to the minus 3t u of t as of such. So yeah, this. Alright, so let me make sure this was so this was. Alright, let's go. X of t was equal to, backtrack a little bit to make sure I have this equation, e to the minus t and e. So this is e to the minus 2t u of t plus e to the minus 3t of t. And using the Laplace table for this, and we transfer this to x of s, this becomes 1 divided by s plus 2 plus 1 divided by s plus 3. And to obtain the region of convergence, we basically watch the denominators here and equate them to 0 to figure out what value they're going to be in order to obtain this. So we watch this first part here, regions of convergence, which I'm going to ROC. This is going to be when the real part of s, in this case, is going to be more than minus 2. The reason for this is that we say s plus 2 here is more than 0, so we get s being more than negative 2. And then the region of convergence here for this part is when the real part of s here is going to be more than negative 3. Now, because minus 2 here, it's more than minus 3 because it's a negative range, there's some overlap. So, because there's an overlap, we will choose the bigger value here for our region of convergence. So, region of convergence for x of s here is the real part of s being more than minus 2. The pose zero plot for this, so if I have to do the pose zero plot for this, this means I want to expand this out accordingly. So if I expand this out, you get 2s plus 5 divided by s plus 2 into s plus 3. And if we watch the numerator here, this is going to be s equal to minus 5 divided by 2. And that will basically be the value of the 0, because numerator roots are zeros, denominator roots are poles. So if we draw the pose zero plot for this, the x-axis here is going to be real, and the y-axis here is going to be imaginary. Our 0 here was minus 5 on 2, that's basically negative 2.5. So then minus 2 here and minus 3. So we'll have a 0 here representing that s equals to negative 5 on 2. And then our poles here would be the roots of the denominator, which is going to be s equals to negative 2 and s equals to negative 3. And the poles are basically represented by x's here. And our region of convergence, in this case, is because we need to take the bigger version or the bigger value of the root, and we're saying that it's more than, it's going to be all of this pass here on the right hand side. So it actually gives us the region of convergence here accordingly for question 11 part 1. So let's actually watch this for question 11 part 2 now, which was basically e to the 2t u of t plus e to the minus 3t, e2t e minus 3. So the next question, which was part 2, was x of t is equal to e to the 2t t plus e to the minus 3t u of t. So that was correct. Right, yep, that was correct. If we take the x of s of this, so we get this into the Laplace transform, this here is going to be 1 into s minus 2 plus, typically if we didn't have this u of t signal here, this would transform to 1 over s plus 3. And we basically will say this is u of s. But, however, let's watch the Laplace transform table here to see why this won't be this in this case. It's supposed to be on the Laplace transform table. If it's not on the Laplace transform table, I'll explain to you why this is the case. Alright, so it's not on the Laplace transform table, so that's not going to help my explanation. So, the unit step here, let's watch our u of t signal graphically. We basically know the unit step here is going to be 0 before time equals 0, and then it jumps to 1 here accordingly, time more than equal to 0. And when we watch our unit step here transform into the Laplace domain, it's basically 1 on s. But the reason why it's 1 on s is that for this section here, for where the value is 1, and now I can actually use the Laplace transform table to explain this to you. If we watch our Laplace transform table here, for a constant value of 1, we have the Laplace transform here being 1 divided by s. But, however, for when it's 0 here, in this particular case, the transform is just going to be 0. Because it comes like if it's just 0 divided by s gives us a value of 0. So this transform only holds true for when we have t more than equal to 0. And the reason for this being, this is what we refer to as the one-sided Laplace transform, which we've been using throughout the entire course so far. If we're not dealing with the two-sided Laplace transform, we're only dealing with the one-sided Laplace transform. So, because we're dealing with the one-sided Laplace transform here, in this particular case, we have e to the minus 3t of u of t. That e to the minus 3t here, and let's see if I actually can plot this for you. So there's going to be exponent of e to the minus 3 by x. So watch what happens here, is that basically when we have the exponent value here being valid for in between 1 and 1 here, but everything else here is just going to be on the left hand side. And because everything has on the left hand side, if we multiply this by the unit step, this means everything here is just going to be 0. And then at this point here, it's just going to be, we're going to say here that's going to be just a value of 1 being multiplied by e to the minus 3 here, t here, for just only this point. Let's watch back our equation here. Okay. Right. So in this particular case, anything for t less than 0 will just be 0. Everything for t more than equal to 0, we actually do have an associated Laplace transform. So just for that case in between 0 and 1, the associated Laplace transform will be 1 divided by s plus 3. And then at this point, we watch our denominators here to determine our region of convergence, similar to what we did in our previous question. So the region of convergence here is going to be the real part of S being more than 2. And our region of convergence here is going to be the real part of S being more than minus 3. Now, in this case, the value of 2 here being more than the value of negative 3, we're going with the bigger value. So as of such, regions of convergence of x of s is the real part of s being more than 2. So let me erase this unit step illustration here because I'm going to have to expand on the equation to show you guys the pole zero plot. So this here, basically, our denominator will become s minus 2, so s plus 3. Our numerator would be s plus 3 plus s minus 2. So that gives us 2s plus 1. That means our 0 of x of s would be that s is equal to minus 1 divided by 2. And our poles here would be, bring this up, poles of x of s be at s equal to 2 and minus 3. And let's do our pole zero plot here only. There's going to be real, there will be imaginary, and say this was at 1. Our 0 here will lie in between minus 1 and 0 only. And so we had minus 3. That would be one of our poles. This here will be at 2. That'll be our next pole. And for the entire system, because we say that the region of convergence is going to be for the real part of s being more than 2, it's going to be everything on the right hand side here in our pole zero plot. So that basically brings us to the end of question 11 regarding how do we obtain our pole zero plots and our region of convergence as of such. So region of convergence is basically just taking the bigger value of s on the denominator and saying for that bigger value, the region of convergence is going to be s more than whatever that value is. When you do the pole zero plot, you basically need to make sure that you expand out your s components here into multiplication of the 2 on the denominator. That way you can get a 0 component here, as well as your pole components as of such. And in the pole zero plot, The axes are real for the x-axis and imaginary on the y-axis. And the zeros are represented by circles or dots, and the poles are represented by x's or such. And then you just draw your line accordingly, and if it's more than, you shade to the right hand side. If for some weird reason it's less than, you shade to the left hand side accordingly as of such. And that's going to be your region of convergence and your pole zero plot as accordingly. Are there any questions regarding the solutions for question 11? Alright, so the last question we'll be doing today would be question 12. And question 12 basically gives us an f1 of x signal and an f2 of x signal here as of such. Alright, guys, give me 1 second. I need to take a phone call here. Alright guys, sorry about that. Okay, so we're moving on to question 12 here. So question 12 basically gives us an f of 1x signal here and an f of 2x signal here. And we need to find the convolution of these signals as of such. So I want to carry this across because I'm going to need the signals here for my sketches. And let's clear the whiteboard here. So let's watch our signals here accordingly and figure out how we're actually going to start doing this convolution. So our first step, it would be to convert our f1 and f2 x of signals here into f1 tau and f2 tau as of such. So we'll have f1 tau being represented here as being in between and here, and this part was 0.5, this was 1.5, and the magnitude here was -2, so this will become tau, and the signal we're going to be flipping will be f2 of tau, and in this particular case, when we watched it here, and we watched it with respect to tau, this was at -1, going up to a value of 6 and ending at a value of 2 here accordingly. The x-intercept here will be at 2. So because we're dealing with a f of 2 tau signal here, we need to get our equation here for this straight line. So we need to know what's the gradient of the line here and what's going to be our x-intercept as such. So because the equation of the line here is going to be y equals mx plus c. So we need to solve for m first, being our gradient, and to do that we're going to have to take the difference in y values divided by the difference in x values. So in this case, we start with the rightmost y value, so we want to say 6 minus 0, and we're going to say 2 minus 1, which will give us 6 divided by 3 close to 2. So we get y is equal to 2x plus c, and then we can just substitute in one of the coordinates here to solve for c. So let's say when y is equal to 0, 2 minus 1 plus c. So that means c here is equal to 2. So the equation of this line here is going to be 2 tau plus 2. Because we changed the axis from x to tau. So now we have to make sure that this flips here accordingly. The f2 of minus tau. And what f2 of minus tau will look like here is that we now have a value of 1 here, or the value of minus 2 here. And it comes like we just flipped the entire signal horizontally. So we'll still be crossing at this 2 points here, and our maximum value here will still be at 6. But it'll come like, well, ignore the squiggly line, we know that's a straight line. It'll come like the signal will look like this. And in flipping this signal, this equation here of this line is going to change accordingly. Because we saw here for this equation it's going to be 2 tau plus 2. But in flipping this, this now becomes, the equation line here will become minus 2 tau plus 2. At least that's what I think it is, and we can verify the equation of the line here as of such. So we know the gradient is going to be minus 2 accordingly, because it's just basically going from upward direction to the negative direction. So basically say y is equal to 2x plus c, and let's substitute in value here, so it's going to be 0, and x here is going to be 1, 2 plus c. So c here is going to be minus 2. Alright, so I was wrong with the equation of the line. Means the entire equation here is going to change accordingly. So that minus sign. So instead of this being 2 tau plus 2, negative 2 tau plus 2, is going to be 2 tau minus 2 here. Nope, whoops, my bad, it's still 2 tau plus 2. I'll show you why. Go to 2x plus c minus 2x plus c. Let's substitute in this coordinate here. So this is going to be 0 minus 2 into 1 plus c. C is still equal to 2, right? Yeah, that's correct. So we just basically just switch the tau value to minus tau and doing our flip here. And then we need to make this into f of 2 of t minus tau. So in making this into f of 2 of t minus tau, oh, oops, we no longer have a y-axis because this is a sliding signal. So this equation here becomes -2, and it comes like if we just add tau over here, we add t here. So this is t plus tau plus t, sorry, plus 2. And this here will become t minus 2, and this here will become t plus 1. I just want to make sure this was correct. Right, yep, that's correct. Alright, so now that we actually have our f of 2t minus tau graph here, and we have our f of 1 tau graph here, we can actually start our convolution as of such. So let's start with case 1. So case 1 would be where we have no overlap between the two signals. And in drawing our graph here, this would be between 0.5 and 5. This was f1 tau, and in this case, let's just draw a signal here. For f2 of tau, can be +1 and b minus 2 here. f2 minus tau. So, because there's no overlap here, we say that t plus 1 here is less than 0.5. So t is going to be less than negative 0.5. And then no overlap means y of t here is going to be 0. Watch case 2 now. And we're going to redraw our graphs here accordingly. And let's draw here where we now start to actually intercept inside our f1 of tau signal. So this here was c that t plus 1. This here is t minus 2 being f2 of t minus tau here. And our overlap between the two signals in this part here only. Yes, sorry. Yeah. So this part here is going to be t. Yeah. Thanks for that correction. T is going to be less than 1.5. Is it? No. It's t less than 0.5. Okay, this will now become 0.5 minus 1. So, yeah. Negative 0.5. Yeah. No, that's correct. Because here it's positive 0.5. So it's positive a half minus a 1. So that's just going to give us negative 0.5. Yeah. Case 1 here, the value is correct. Okay. The case 2 on the other hand, let's actually start evaluating this accordingly. So our time range here is t plus 1 has passed 0.5. So we say t plus 1 more than equal to 0.5. So t here is going to be more than and equal to negative 0.5. But t plus 1 here has not hit the value of 1.5. So t here will end up being less than 0.5 here. And if we combine the t ranges here, we get 0.5 minus 0.5 is less than equal to t less than 0.5. Now we also need to keep in mind that this straight line equation here, we calculated, was minus 2 into tau plus t plus 2. So this was minus 2 into tau plus t plus 2 for that equation. And magnitude here was minus 2. So, in solving for y of t, this is going to be the integral of the two signals, f1 tau, f2 t minus tau d tau. And if we watch the limits of our integrals here, or our overlap, it's going to be t plus 1 being our uppermost limit and 0.5 here being our lowermost limit. So it's going to be t plus 1, 0.5. f1 of tau here was basically a value of minus 2. And then f2t minus tau here, we need the value of the equation for our straight line, which is going to be minus 2. I want to expand this out accordingly. So it's going to be minus 2 tau plus 2t plus 2 into d tau. Let's expand this out. T plus 1, 5 into 4 tau plus, so it's going to be plus, it's going to be minus 40 minus 4 d tau. And in this particular case, t here, because we integrate with respect to tau, t is treated as a constant. So when we actually conduct our integral here, this comes such that it is you'll get 2 tau squared minus 2t tau minus 4 tau in t plus 1 and 0.5. So the question is, why is this minus 2 into brackets tau plus t instead of minus 2t minus tau? That would be when we actually derive the equation of the line all the way up. So we knew that for just f of 2 of tau, when we derived the equation, it was 2 tau plus 2. And when we switch this to f of 2 minus tau, that comes like we just only affect the tau value here. So that becomes minus 2 tau, and the plus 2 here remains the same. And because this is already f of 2 minus tau, when we add t here accordingly, that means everywhere that we had minus tau, now becomes basically t minus tau. So let's make sure I'm doing the correct thing here. Alright, so let me just make sure that was actually correct. If I move on. Right. All right, yeah, okay. So in this particular case, because it was factorized, because we had the minus sign on the outside here, this comes like if we just take the tau value here and we say, okay, it's going to be t minus tau, and we just pull out that negative sign of such when we did factorization. So I understand what you're talking about here. It comes like you're wondering, okay, why does it become, it's a minus 2 tau plus 2. Why does it become this value here instead of minus 2t minus tau? So when you expand this out here accordingly, this is going to be minus 2 tau minus 2t plus 2. And let's see if that actually holds true. So, all right. So I'm trying to make sure that's question here actually correct. So this here, all right. So let's see. This is basically 2 into minus tau plus 2, and then when we expand this into t minus tau, it comes like this: 2 tau plus t plus 2 minus 2 tau 2t 2. Basically, that's what you're saying. And make sure this was actually correct. Yes, actually is correct. Right, nice. Thanks for pointing that out. So this here is going to be minus tau here. Be minus 2 into t minus tau. Right, yeah. Thanks for pointing that out. Yep. Actually is one correction that we had to watch in particular, because I did not factorize in this part here where we just add minus tau here and then we just add in t as of such. Get that. So this will become minus 2 t minus tau here plus 2. Alright, yeah, that's correct. Alright, and means this equation here will change accordingly. T minus tau. Correct. Because that now becomes that, means our equation here changes accordingly. So this now becomes, right, that means all our equations here change accordingly. Nice. So this now becomes minus 2t plus 2 tau plus 2. If we expand this out, 1, 0.5, get 40 minus 4 tau minus 4 d tau. We integrate this, get 4t tau minus 2 tau squared 4 tau t plus 1 and 5. And then if we substitute in our values here accordingly, for t plus 1 minus 2 into t plus 1 squared minus 4 into t plus 1. And then we'll have minus, substituting for tau here, so this will become 2t minus 2 into 0.5 squared minus 2, and we're going to have to use a calculator here at this point. Bring this up here. The Alright, so in calculating this out, what we get here is that we have 2t squared minus 6t minus 3.5. So yeah, it's actually going to be minus 2t minus tau, which I actually did here. So I went back through the correction for you guys to understand why we got this. So let's watch up f of 2 minus tau signal here. When we calculated the equation for the line here, this was minus 2 tau plus 2, right? And when we carry this across here, this is basically 2 minus tau plus 2. When we convert this to t minus tau here, this comes like to just minus tau plus t. So everywhere we had minus tau, it now becomes minus tau plus t as of such. And if we rearrange this accordingly, this becomes minus 2, if we pull this out, into t minus tau plus 2 accordingly. So this comes like if we just rearrange this into t minus tau, and now we have this minus 2 here accordingly as of such, and we get plus 2. So I'll rearrange the work in here for you guys so that way you can see what I'm talking about. So f of 2 minus tau here was equal to 2 into minus tau here plus 2. And then we want to say this is going to be f of 2 here into minus tau plus t. Now becomes 2 into minus tau plus t plus 2. And we can rearrange this accordingly. Minus 2 here, sorry. this becomes 2 into t minus tau plus 2. Right, okay. I see what you guys were talking about. Alright, yeah. Alright, yeah. So the correction here basically is that we have f of 2 of minus tau. When we got our equation here, it was minus 2 tau plus 2. And if we arrange this to minus tau, we isolate the minus tau here accordingly. This comes like if it's 2 multiplied by negative tau plus 2. So because we have the negative tau here, and we just add t here accordingly, because it comes like if it's just t minus tau, and we just invert this accordingly, it's now equal to 2 of minus tau plus t plus 2. And then if we flip this accordingly, it's going to be 2 into t minus tau plus 2. Alright, yeah, that's correct. This is actually the correct equation here as of such. So this actually is correct. So that means, yeah, the working I just loaded, I'm going to have to redo that over, because this is no longer minus 2t minus tau, positive 2t minus tau for the actual equation. Right, yeah. So yeah, all this integral stuff, I'm going to have to redo it, because I calculated the line wrong. So I'll go back through calculating the line just now. Let me just finish up the integral here. Because I don't have to explain that over for you guys. This no longer holds true. Alright, good. Alright, so let's explain back that line equation that's given us some trouble. Alright, so the f of 2, yeah, that's what I'm going to explain to you guys now. So f of 2 tau here, when we calculated the equation for this line, we got the gradient here equal to 2. And we got our x-intercept here being positive 2. So we got 2 tau plus 2. When we flip this to f of 2 minus tau, this here becomes negative 2 tau plus 2. And if we watch the work in here, this comes like if we say 2 multiplied by negative tau here of plus 2. So the negative sign here basically got factored into the brackets. Because we have f of 2 minus tau here, and we convert this to f of 2 minus tau plus t, which is basically t minus tau, just in the reverse fashion, this now becomes such that we just add t here accordingly in the brackets. So this now, because of minus tau here, this becomes minus tau plus t. So we have 2 here of minus tau plus t in the brackets here, plus 2. And if we just rearrange this accordingly, this becomes 2 into t minus tau here, plus 2. So this negative tau here is factorized into the brackets. Because if we expand this out accordingly, we'll get back minus 2 tau here, plus 2t, plus 2 as of such. So case 1 remains true because there's no overlap. And case 2 is where we actually started with our working. So now that we actually start with our working here for case 2, and we caught on to that error early, thanks for that, we can actually start doing the correct integration process here as of such. So if we expand out our f of 2t minus tau equation here, this becomes 2t minus 2 tau plus 2, and this is with respect to d tau. And then we multiply this out accordingly, and let me just make sure. Alright, yep, that's correct. Alright, so we multiply those accordingly, and we get minus 4t plus 4 tau minus 4 respective d tau. And then we perform our integration here. So this becomes minus 4t tau plus 2 tau squared minus 4 tau in between t plus 1 and 0.5. So this becomes minus 4t into t plus 1, because remember we're doing the limit evaluation with respect to tau, plus 2 into t plus 1 all squared minus 4 into t plus 1 minus and let's open our brackets here into minus 4t, and that's made multiplied by 0.5, so this becomes minus 2t here, plus 2 to 0.5 all squared minus 4 to 0.5, and we evaluate this out, so I'm going to have to pull up my calculator to evaluate this again. So let's see how I'm doing this. For that plus that minus that minus plus that. Right, so calculating this becomes minus 2t squared minus 2t minus 0.5. So that basically gives us the answer for case 2. Let's go on to case 3 here. So for case 3, because we have the width of our f of 2 t minus tau signal here being basically a width of 3 on the denominator, sorry, not the denominator, on the x-axis, there will be an odd case here where the f of 2 t minus tau signal will totally encapsulate the f of 1 tau signal as of such. And for that particular case, we need to make sure that we actually draw this out accordingly to make sure it encompasses it as of such, in order to make sure that we compensate for it. So in compensating for this, basically when we do this, we basically evaluate this saying that the t plus 1 here, it's already crossed the 1.5 value. So this here is going to be t plus 1 is more than equal to 1.5. So t here will be more than equal to 0.5. But in this case as well, we want to watch our t minus 2 value here, and our t minus 2 value here is less than 0.5. So t minus 2 here is less than 0.5. So t here is going to be less than 2.5. And when we actually calculate out, alright, so whoops, one further thing we have to do here, so we can combine our t ranges here. So this will be 0.5 less than equal to t less than 2.5. And then we can actually perform an integration as of such. So this will be y of t is equal to the integral of, and we watch our overlap here. So this will be 1.5 and 0.5 for limits into -2. And then we put back in our equation here accordingly, which we had for case 2. Now that we had the correct equation, so it's going to be 2t minus 2 tau plus 2. Check the d tau. And we already did the math here for this in case 2. So because we already did the integral part here and it was just we had the substitute, then this will just end up resolving to minus 4t tau plus 2t squared, 2 tau squared, sorry, minus 4 tau. So minus 4t tau, that's going to be minus 4t tau plus 2 tau squared minus 4 tau. Our limit here is going to be in between 1.5 and 0.5. And then when we evaluate this, we get an answer of minus 4t. So this will be our answer for case 3. Case 4, draw back our graph here accordingly. All right. For case 4, we slide the signal again. And for this case, we watch our t minus 2 intercept. So we see that t minus 2 here has crossed 0.5. So t here will be equal to 2, more than equal to 2.5. But t minus 2 here is also less than 1.5. So as of such, t here will be less than 3.5. And when we combine our t ranges, we get it in between 2.5 and 3.5 accordingly. And then our y of t equation here, when we do our integral, will be in between 1.5 and t minus 2. For our limits, minus 2 into the same equation that we had before, which is 2t minus 2 tau plus 2. And we basically do the same integration as before, and we'll get an answer coming down to the same thing as before, because this is basically the same integration throughout the entire thing. So we get minus 4 t tau plus 2 tau squared minus 4 tau between 1.5 and t minus 2. When you evaluate that out, you'll get 2t squared minus 2t minus 17.5. And for our last case, it will be case 5. There's no overlap here, but we still need to figure out what's our t range. So we say t minus 2, in this case, has crossed the 1.5 here of f1 of tau. So more than equal to 1.5. So t here is going to be more than equal 3.5. And there's no overlap. So y of t here is basically equal to 0. And when we combine our answers, for y of t here, we have 0 for t less than negative 0.5, then minus 2t squared minus 2t minus 0.5 for a time range of negative 0.5 less than equal to t less than 0.5. Then we have minus 4t here for a time range of 0.5 less than equal to t less than 2.5. Then we have 2t squared minus 2t minus 17.5 here for a time range of 2.5 less than equal to t less than 3.5. And then we have 0 here to t more than equal to 3. Which basically brings us to the end of our convolution question. So the trick behind this that would basically tie you up, and what we saw in the early beginning, was resolving that straight line equation for f of 2t minus tau. And resolving that up front, making sure that we had the correct equation, all the cases basically just flowed into one another because it was basically the same thing being integrated, just with different limits. So I'm scrolling back up here to get to where we resolved the line. So just to recap it in particular, we start with f of 2 tau here, and we calculated the equation of the line here by finding the gradient and then finding the c-intercept by substituting the coordinates. So we got this equal to 2 tau plus 2. When we switch this from tau to minus tau, this becomes minus 2 tau plus 2. And if we isolate that minus tau here, it will become 2 multiplied by negative tau here in brackets plus 2. When we move this towards t minus tau, this comes like we just say minus tau plus t. So this minus tau in the brackets here now just adds t accordingly. So this becomes 2 into minus tau plus t in brackets plus 2 here accordingly. And then we can rearrange this accordingly and to make t here the forefront here. So we just flip this accordingly. So we get 2 in brackets here, t minus tau plus 2. And for case 1, there was no overlap, but we still need to figure out the time range here. So t plus 1 here was less than 0.5, so we got the time range here accordingly for t. No overlap, meaning y of t here was 0. For case 2, because we had an overlap here where the t plus 1 factor went more than 0.5, we say that it's more than equal to 0.5, so we solved that out, but t plus 1 here was still less than 1.5, so we also solved for this. And we got our combined time range here. When we did our integration for the overlap, the uppermost limit and the lowermost limit here was t plus 1 and 0.5. F1 of tau here was just -2. And F2 of t minus tau here was 2 in the brackets t minus tau plus 2. And we expanded this out accordingly. We got 2t minus 2 tau plus 2 here, d tau. And then we expanded it and we went about doing our integration. Because this with respect to d tau, the t's here basically are treated as constants. So minus 40 here will become minus 40 tau. 40 here, when we integrate this, will be 4t squared divided by 2. So that's why we got 2 tau squared. Sorry, 4 tau squared here divided by 2. That's why we got 2 tau squared here. And minus 4 here became minus 4 tau. We had our limits. We substituted into the equation accordingly. And we got our resultant t equation. Then we saw here for case 3 and case 4, it basically was the same integration that was going on here, just with different limits. So our work was already done for us. For doing the integral part, we just needed to substitute in different limits and we got a different equation here. Same thing with evaluating our time ranges. We saw that t plus 1 went more than 1.5, so we had more than equal to 1.5. Although t minus 2 intercept here was less than 0.5, so we solved for that accordingly. Case 4, we did the same integral again, just the limits changed to 1.5 and t minus 2 for our integral. Our time ranges here were calculated with respect to t minus 2. And then case 5 here basically had no overlap. So this was y of t equals 0. And we got our time range here accordingly as of such. So I will post up the solutions accordingly for the rest of the problem sets. And I will also post up next week's lectures as of such. But unfortunately, that's all the time I have for today, and I will basically take any questions via email or comments in the video, so that way I can answer them accordingly as of such. So, I'm sorry that I actually have to end now, but I actually have to take care of a small emergency that's going on outside. So, until then, take care, be safe, and I'll see you guys soon. Later.